Let me say a couple of things about the test first. First of all, as a class, as a whole, you all did pretty well. It was an improvement over the first exam, which the first exam wasn't terrible anyway, but it was an improvement over that even. So you all have another bite at the apple, as I said in the email. So what I mean is, after this exam as well, so you've got up until we have the final exam, just come by my office and say, hey, I want to do the assessment thing, and we'll do kind of an assessment exit interview. We'll see where you're at, maybe try to estimate what you need to kind of finish off the course, the way you want to finish it off, that kind of an exit interview, kind of in-game strategy. You can do this anytime up to when I get the final exam. I would recommend that you do this earlier rather than later, especially if you've got concerns that, you know, maybe you're not where you want to be in the class. The sooner we can have this discussion, the better. Again, it's optional, but at 3 points, you might as well do it. So, okay, any questions before we get rolling? All right. So before we move on to the next chapter and talk a little bit about integers, I did want to touch up on a couple of things at the end of the group theory part. I only did like half of this theorem, and then I'm going to give you one more, and then we'll kind of move on. Let G be a group, and N in G, then this theorem, we claim that N is normal in G. Is the kernel of homomorphism with domain G. And what we showed last time, although it has been remembered, so it's not going to hurt anything. Actually, let me do it this way, because this is what I've already proved for you, but it wouldn't hurt to review it. So suppose that N is the kernel of some homomorphism with domain G. Now, we claim that N is one of these crazy normal subgroups, right? So we need to show N is normal in G. Anybody remember what this means? One of the equivalent definitions, normal? Yeah, the left and right cosections are the same way. There's another way to put this that I think is more convenient for the purposes of proof. So that is if N is in N and G is in G, then G inverse in G is still an N. Remember that when you conjugate something, when you put G inverse in G, it's still an N. By the way, this kind of thing, this G inverse in G, might look familiar from linear algebra. Did you ever look at matrices that are in form P inverse AP, right? These are equivalent. This is kind of a big kind of theme in this sort of mathematics. Okay, so this is all we got to do. We got to show that if N is in N, then this conjugate of N is in N. And what does it mean for N to be N? then f of n is the identity of H. Everybody agree? That's what it means to be in the kernel. It means it zaps that in to the identity over an H, right? So scope this out. Let's see what happens to this end. Well, don't know much, but I know that this is a homomorphism, right? And so F of G inverse NG, I can break up this way. Gotta love them homomorphisms, right? Now, here's my Oreo. What can I say about the creamy filling? F of N is, yeah, correct. Which means I can collapse this like an accordion here. And now we'll do the homomorphism thing again. What's G inverse of G? Well, that's always the identity. And what, if you have a homomorphism, what does it do to the identity of the domain? It takes it to the identity over in the range. So G inverse NG is in the kernel F, which is, so there's one direction. We've shown that that the kernel is in fact normal. Agree? Now, the other direction, we want to show that if N is normal in G, then it's the kernel of some homomorphism. And this one I can just build. Y'all remember this one here? So I'm going to build this homomorphism here. Y'all remember this thing? This is the set of left cosets, right? Remember what this is? This is a set of left cosets, Gn, with multiplication given by G1 n times G2 n is G1, G2 n. Y'all remember this one? This quotient group thing? We went to some pains before spring break to prove that that multiplication is well defined if and only if n was a normal subgroup, right? This is a homomorphism because pi of G1, well, I got to tell you how this works in the first place. Pi of G is Gn. That's the way this homomorphism works. Remember, in math, if it ain't easy, don't do it. What am I going to do? I need to input some element of G and output a coset. Well, this is the easiest way to do it, right? Notice that pi of G1, G2 is G1, G2n, which is by definition G1n, G2n, because that's the way that we multiply these things, which is pi of G1, pi of G2. So pi is a homomorphism. And all it remains to do is show that the kernel is in. Everybody okay with that? And that'll finish up the theorem because here is a homomorphism with domain G. If the kernel of this is exactly in, then we're good to go. Now, I'm making this wild claim here. So what do I have to do? I have to show that the kernel is contained in N and N is contained in the kernel. I got to show they contain each other. So let's do that. Then pi of x, x n the identity. Yeah. So in other words, the coset xn should be the same thing as the coset identity of n, which means that E inverse x, so the kernel of I is contained in n. Because if the coset xn is equal to en, remember what that means is E inverse x has to be in n. And E inverses, of course. E. Any questions on that question? On the other hand, I want to show that anything in n is in the kernel of pi. So but so now I have that n is contained in the kernel of pi. Any questions on this?
How did you get like the inverse of d x is equal to x is contained in?
Well, because remember, one of the things that we had earlier was we had that equivalence relation. If H is a subgroup of G, then AH, when are these two left cosets equal, then this is true if and only if B inverse A is in H. Right? That was one of those things about cosets we proved. So here we have that these two are the same, so that means that E inverse X must be. Okay. Any other questions? Okay. The final bit in this group theory thing, this is a very important theorem. There's actually a number of these sort of numbered isomorphism theorems. I'm just going to give you the first isomorphism theorem because it's sort of the daddy mac of the isomorphism theorems in the sense that any others that you read about actually follow from it. This is used in the proof theorem. I guess this is 5 or 7. Isomorphism. Remember, an isomorphism is a very special homomorphism. A homomorphism is just a function from one group to the other that preserves the structure, right? Like the logarithm and things like this that we looked at. An isomorphism is a homomorphism that is also both one-to-one and onto. So it's a bijection. So it's even stronger than being an isomorphism. And this shows you, this first isomorphism theorem, shows you how to build an isomorphism from a homomorphism in the following sense. Let P from G to H be a homomorphism. Any homomorphism, like, for example, this one that we did here, or the function from Z to Z mod N, where you take your input as K and you reduce mod N, any homomorphism you can think of, then B induces an isomorphism. B bar then there's an isomorph. So here's the way this works. Your input, so you've got this homomorphism here. This gives you a homomorphism from this different group, G modulo the kernel of phi, onto whatever the image was over in H. Whatever is covered over here in H is a subgroup of H, right? For example, if phi was onto in the first place, this would be all of H. But if it's not onto, this will be some small part of H. And I'll tell you in the theorem the way the homomorphism works. So maybe this will make the notation less confusing. So let n be the kernel of phi. So a typical element here is Gn, right? Because this is a coset here. This is phi. Okay. And in fact, this right here, I claim this is what we need. So I'm going to verify that this works. Given we now have a new function well, actually, where n is kernel phi given by bar of n. Now, there's something that we have to consider very carefully here. There's a subtle point right here that we have to check before we can do anything. Actually, most of the proof of this is easy. The first subtle part is perhaps the most difficult. Does anybody know what we have to check here? What's a homomorphism? What is a homomorphism first and foremost? Right, it's got, well, we hope it's got this domain in this range, right? But it is a what? Homomorphism is very fancy. It's a blank that has some special properties. Well, first and foremost, and you see this is easy to overlook, it's a function, isn't it? You got to input something in G mod n, and it's got to barf out something in the image of phi, right? That's what I'm claiming is going on. Now, what is it about a function that makes it a function?
There's only one output for each input.
Right, right. For every input, there's only one output. That's the big thing about a function, right? This is problematic. Can anybody explain to me what we might, potential hazard here? What is G mod n itself? Or Gn? It's a coset, isn't it? Right? So for example, so let me kind of give you an example so we'll think about it. If we had Z mod 2Z, okay, there are two cosets here. The evens and the odds. Everybody agree with that? Now, this thing that I'm inputting isn't just a single element, it's a set, right? It's a coset. and it's supposed to output something here. Now, the way this function works is it takes an element out of that set and plugs it in. Everybody agree with that? It looks at this coset Gn, and it picks out G, and it plugs it into this function, right? Now, if this is the input coset right here, I might pick 2 as my representative, right? You might pick 6. You might pick 10. We better get the same answer, right? For the input coset, it's got many representatives. This has infinitely many representatives, right? But you're only plugging in one representative to this function. You better get the same freaking answer no matter what representative you plug in, or this isn't even a function. Everybody, I know it's a little hard to wrap your head around, but does everybody kind of get that, right? So we got to test that. We got to make sure that no matter what representative we elect, we get the same answer over here. Yes, sir.
So are they supposed to be the same?
The output has to be the same, no matter what. So for example, if this is the coset that's all the even integers, you might elect number 2 to plug into this function. And I might elect 18 to plug into this function. Your output and my output has to agree. Otherwise, it's not a function, right? Because what we're plugging in is a coset, but we pick a representative to get the output. Yes?
So every representative from that coset is considered the same input?
That is correct. And that's the problem. That's why you got to check it. Because, like I said, I might put in 2, you might put in 18, somebody else might put in -22. It's got to give you the same output here. Otherwise, it's trash. It's not a function, right? We got to check this. So let's suppose, for the sake of argument, let's make sure that this is what we call well-definedness. This makes it's a function. Is this function well-defined? So let's test well-definedness. And I don't know if you should write that down because I probably just made that work completely up. But let's suppose that we have x10 equals y. Right? This is equivalent to me saying I'm electing the representative x out of that coset, and you're electing y. Right? We got to make sure that this is the same thing here. Can somebody tell me what this means about y inverse x? If x and y represent the same coset, what is true about y inverse x?
It's contained in it.
It must be contained in n. And let me remind you, just for giggles, that n is the kernel of phi. Everybody okay with that? So what does this mean? If y inverse x is in the kernel of phi, what does that mean about phi of y inverse x? It must go to the identity, mustn't it? Well, I'll just write E because, yeah, image of phi. Now let me break this apart here. This is phi of y inverse, phi of x. And let me write one more line. This is phi of y inverse, phi of x. Everybody agree? You gotta love homomorphisms because remember, I can pull all integer powers out. Now multiply both sides of this equation by phi of y on the whatever side this is left, and I get phi of y equals phi of y inverse, phi of x. And of course, those two animals cancel. Whatever phi of y is, that's its inverse. And I get phi of y of x. So phi bar of yn equals phi bar of x. And big smile, because that means that this function is well defined. Didn't matter what representative we picked, we got the same amount. Everybody okay with that so far? Folks, that's the hump. That's the big part. Everything else is fairly easy to show. Let me go through it. So how does the rest of this go? So now I know that this is a function, it's well defined. Right? Okay, what else do I need to show? I know phi bar is well defined, I got that licked. I need to show that phi bar is a homomorphism. So let's check that. If you look at phi bar of xn, yn, this is phi bar of xy n. Everybody agree with that? Because I could smash those two together. That's the way the multiplication works there. And what does my rule tell me? Well, let's see. My rule tells me that phi of little letter times n is phi of x1. And I don't know much, but I know that phi without the hat on it is a homomorphism. That was my assumption in the first place. So this is phi of x, phi of y. And now going back to the definition here. Okay, so it's a homomorphism, right? Because phi bar of this coset times this coset is phi bar of this coset, phi bar of the second coset. Got that. Let's see. It has to be an isomorphism, so I need to show that it's 1-to-1 and onto. So let me show that it's 1-to-1 first. Suppose okay, what I need to do is I need to show that this thing and this thing are equal, right? Everybody agree with that? That's what it means to be 1-to-1. Okay, so what does this mean? And I forgot to put my little hat on. I apologize for that. What this means which means, let me put this on the other side here. Phi of y inverse, phi of x is the identity. But this means that phi of y inverse, I just slipped that inverse back inside of there, which is phi y inverse x. So phi of y inverse x is the identity. So I can conclude that y inverse x, what can I say? If phi of y inverse x is the identity, what does that mean about y inverse x? It's in the kernel. Good, 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 good. But if y inverse x is in n, that means that xn equals y. So phi bar. Because this implies that xn equals y. And onto is actually easy because all we need to do is show that the image is covered. And that's not a problem because, well, I don't know, H being the image of phi. So there exists X and G such that H is phi of X. That's what it means to be in the image. But this is phi bar of Xn. And so anything in H is covered. So it's not. Okay. Any questions on this? Questions? Okay. Yes, sir.
So the reason that y inverse x being in the kernel ensures that x and y are equal, because that would mean that y inverse x must be the identity.
No. A little caution we need here, because y inverse x is in the kernel. That means that this is true if and only if the coset xn is the coset yn. It doesn't mean that x and y are equal. It just means that y inverse x is actually, it means they represent the same coset. Right? But that's all we need here, because our input for phi bar were cosets. Right? Is that okay? Okay, so what we're going to do now is I'm going to start looking at some more properties. Now you're going to see fairly soon in this section why I did a little bit of group theory first, because it will make a lot of this stuff here, even though we're going back to the integers, a little bit more, well, it's a little, makes it a little bit easier. We are going to look back at the integers, some basic number theory. Some of you may have heard of some of this stuff before, like Fermat's little theorem and maybe the Euler phi-function. It is going to make some of the problems we've already done in class a lot easier. And we're going to segue into rings, which are basically, we've talked about rings without you knowing about it. It's basically structures where you can add and multiply. And then once we've got that tied up, we're going to get heavy into a number of applications of all this. Okay. Integers revisited and basic number theory. And pretty much. First, we're going to start off with on modular arithmetic. So we're going to do what might be construed as basic properties of some of the integers that you're certainly not going to see, you know, when you first study multiplication tables. And actually, these basic properties allow us to do things like, for example, coding theory. The first is sometimes this is called Euler's totient function. Has anybody ever heard of this? Ever heard of the Euler phi-function or the Euler's totient function before? This will eventually simplify a lot of our lives. Let me tell you what it is. It's a simple idea. Definitely. Let n be a natural number. And as follows. It's a number. So the output is actually a natural number. It is size of the set K such that we'll do this to start a corner. That way. Such that so what it does, so phi n counts numbers between 1 and n inclusive, such that well, let's see, that are relatively prime. So it just counts the numbers between 1 and n that are relatively prime to n. That is, that have no common factor with n other than 1 or minus 1. So for example, it's always good to see a couple of examples here. Let me look at a couple of examples. So this should count the numbers of things between 1 and 1 that are relatively prime to 1. Well, how about 1 itself? That's it. There's only one of these. This counts the numbers between 1 and 2 that are relatively prime to 2. 1 is, 2 is not, so 1. This counts the numbers between 1 and 3, 1, 2, 3 that are relatively prime to 3. Only 3 has a common factor, so there's 2 of these. How about 4? What should that be? Two. The numbers between 1 and 4 that are relatively prime are 1 and 3. There's 2 of them. How about 3 and 5? Good. P of 6 is 1, 2, 3, 4, 5. Looks like this is 2 as well. Anybody want to guess this one? What if you're a prime?
P minus 4.
Exactly. Right. 1, 2, 3. Everything less than a prime is relatively prime to that prime because it's prime, right? It's only factors itself in 1. So the only way that you can pick up a factor in common with a prime up to the prime is for it to be the prime itself. So if you count between 1 and P will have a factor in common, but everything less than it will not. Right? I guess we could go through this by brute force. Let's see. Let's count through 12. 1, 5, 7, 11. Looks like 4. This one's more obnoxious, right? You actually had to do this on one of the homeworks, although it wasn't counted in this term. This is 40. We'll find out a way to do this very quickly. Like, you can count if you like, but we'll find a way to do this quicker later. Any questions so far? Okay, so let me give you a theorem. And the proof of 2 of these is very easy. The proof of the third one I'm not going to do yet because it's going to be easier when I give you something else called the Chinese remainder theorem. But here's some properties of the Euler phi-function. Theorem. Prime. A. We already kind of figured this one out. I don't think we need to prove this really. if you have p to the n power, where it here, I will assume, of course, that n is greater than 1. Then the Euler phi-function, that is the number of things that are between 1 and p to the n that are relatively prime to p, is p to the n minus 1 times p minus 1. By the way, we kind of already figured that one out. Let's see if that connects with our formula here. Let's see. That would be this formula applied to the case where n is 1. And if n is 1, that's p to the 0. And okay, so this apparently this is looking good to me. And C, if the guys listed are distinct primes, then Euler phi of the product AI and AI is greater than or equal to 1. I 1K is the product of phi AI. Let me give you I'll prove that C works for you later, but I'll give you an application of it when I'm done with B. Well, like I said, with the Chinese remainder theorem, we can make B pretty easy. I'll let that do heavy lifting. Why is this true? That relatively prime correct? That's what this function should give us. It's the number of integers between 1 and p to the n that are relatively prime to p to the n. But let me point out that relatively prime to p to the n means relatively prime to p. It's equivalent, right? So, number of integers between 1 and p to the n that are relatively prime to p, right? Because if you share a factor with p to the n, one of those factors has to be p, right? There's no way around it, right? Because the only values of p to the n are p to smaller powers. Everybody cool with that? Now it's easy to count. So between 1 and p to the n, there are p to the n minus 1 multiples. Everybody agree? There's p, 2p, 3p, 4p, etc., all the way up to p to the n minus 1 times p. Everybody agree with that? And so, to get this, the number of things that are relatively prime to this are the total number of integers, which is p to the n, take away the multiples, right? Because if you have all the integers, take away all the multiples of p, what you've got left over are all the things that are relatively prime to p. And if you pull a p to the n minus 1 out of this, you get the desired form. Everybody okay with that? again, another application of counting. Let me give you all a quick application of this. This was kind of a, I wouldn't say this is a hard homework problem, but it was obnoxious because you had to like fight your way through it, figure out, okay, which elements between 0 and 100, between 1 and 100 are relatively prime to 100. Well, so write 100 into prime powers. Now let's apply number C. Number C says, when you do the Euler phi-function to a product of prime powers, you can write that as the product like that. That's what part C says. So I can break it up like that across the relatively prime factors. Agree? Now, to these separate pieces, I will apply B. Okay, so this should be 2 to the 1 power times 2 minus 1 times 5 to the 1 power times 5 minus 1. So that's 2 times 1 times 5 times 4, which is 4. Bang, 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 like that. So now I know, and so here's a consequence of that. The number of units in Z mod 100 is 40. That means the number of zero divisors is 60, right? Okay, any questions on that? Okay, I'm going to give you another theorem that we will spend a little time verifying before we get to the Chinese remainder theorem. And this is a really, really cool theorem. In my setup here, well, suppose we have a positive prime integer. Suppose that GCD of A and N equals 1. And also suppose that X is equivalent to Y. Mod phi n, not mod n, but not like this Euler phi function, mod phi n. Then A to the X is equivalent to A to the Y mod n. By the way, you may not recognize it, but you actually did use this in that homework where we tried to find 8675309 to the 8675309 power. Number 2, Wilson's theorem. Actually, I wanted to be correct in one. N is prime if and only if n minus 1 factorial is equivalent to minus 1 mod n. And number 3, and this is called Euler theorem. This is another one that's central to coding. If GCD of A and P is 1, that is to say, if P doesn't divide A, right? So, because remember, P's a prime. So if A has no factor of P, then A to the P minus 1 power is equivalent to 1 mod P. And this is really, it's kind of magic to watch this work. So for example, GCD of 2 and 13 is 1, of course, 13 is prime. Therefore, 2 to the 12th power is equal to 1 mod 13. And this is like, I love my, that's 4096, not bad. Give it 10. Yeah, this 4096 is, and I haven't done the computation myself, but I guarantee you that this will work out. Let's see, that'd be 4095, 165. Yep. It's a miracle that this works out, and it always does. And like I said, this has important applications in, for example, coding theory. So you might think about that. Do a couple of examples and watch this magic happen, and we'll verify why all this magic works, and then we'll put the tools to use. Any questions? Any questions? All right. Well, don't forget to stop by and talk about the class when you get a chance. Other than that, you all have a good one, and we'll see you on Wednesday.